Today we have a few things. One of the main things is this prototype of our, what we're calling the Camlock heads. This one is an initial design. Currently it's on its second iteration, which should be going into production soon. The main idea behind this iteration is, rather than having the typical bolt pattern on the back of the head in order to disassemble it and clean it, this has a single rotating piece that not only disconnects the internals from the body, it also ejects the internals with some mechanical advantage in order to facilitate the removal process and the cleaning process. This was designed mainly with the wire and cable industry in mind because they have long runs, and in order to meet their production quotas, they need as short a downtime as possible. Now, obviously, a short downtime is beneficial for any industry, so we are filtering this out through all of our offerings as much as we can. Basically, we started with the design criteria of how do we lock this into the head without using any bolts. We took some cues from some other industries. Mainly, this was actually sort of based on the way that fire hose connectors go together. So we looked at how we could make that a bit more robust in order to be able to handle the pressures that are generated in an extrusion head. Fire hoses generally generate somewhere around 100 psi, 200 psi. We're looking at sometimes upwards of 5,000 psi in an extrusion head. So this had to be much more robust, the materials had to be stronger, and the design had to be a little bit more thorough in order to add the margin of safety that's required for this industry. It should be compatible with any of the industries. Like I said, it's mainly for wire and cable, but the tooling that fits into it is the same tooling that fits into every other one of our heads, so it is compatible with any industry. There was a lot of finite element analysis for strength to make sure that the heat treat that we were using was appropriate, the materials that we were using were appropriate, and this, like I said, is the prototype result. The final result that we're hoping will be the production model is currently going through our production shop. And there are a few iterations. In this design, you'll see the locking features inside the body are dowel pins. We found that those didn't have the strength required to have the longevity that we're looking for on this head. So the next model will have machined lugs on the inside, similar to the machined lugs that are on the mating piece. The initial version of this head was a fixed center, which means that there was no adjustment for the concentricity for the tooling. It was simply fixed fine concentricity between the two pieces. We opted for the next version to have concentricity adjustment installed because it's just another factor that adds to the longevity of the head. If there's any wear in the components that might imbalance the flow, you can counteract that with the concentricity adjustment, which gives you much more life out of the tooling. So from start to finish, this was engineered for what we would want to use in the field if we need quick changeovers, longevity, and just good practical usability. Once we started the design, when we had the initial concept down, one of the first things we did was, in order to test to make sure that the material and the geometry of the design was strong enough to handle the pressures, as I mentioned, we use a simulation. We use SolidWorks for the design in CAD, and SolidWorks has a plugin that can do finite element analysis on the materials. So we mainly were focused on these lugs here because that's what's holding back the force, and the lugs on the inside of the head. So one of the things that we actually found through finite element was we initially had 1/4-inch dowel pins inside the body and found that those would shear off at the pressures that we were looking at. So we increased those to 3/8 dowel pins. One interesting thing is that while finite element analysis is very useful and practical for the design and necessary in most cases, it's very difficult to show everything. So one thing that we didn't catch with the finite element analysis was that while the 3/8 dowel pins are strong enough to resist shearing apart, a press fit hole in the body isn't strong enough to withstand the cycle wear from loading and unloading this into the head, and eventually these became loose and it didn't seal anymore. So it's not a drawback to finite element, but it won't do everything. There is still a portion of practical experimental data that you need to get. It is a really good starting point, and it's something that we use quite often when there's any question of material durability or design safety factors that we need to take into account.